Okay, so let's break down generative versus discriminative AI models. Think of it like this. Generative models are like artists. They learn how things are made and can then create entirely new works based on the knowledge. Models like GPT and DALL-E fall into this category. On the other hand, discriminative models are more like judges. They learn to tell the difference between different categories without necessarily understanding what makes each one unique. Image classifiers, for example, are great at spotting a cat in a picture but don't know how cats were created. They're focused on drawing the line that separates them. Okay, let's dive into how these incredibly powerful GPT models actually work. They're built on the transformer architecture, which is a significant departure from older methods. Think of it as having both an encoder and a decoder, but GPT uses just the decoder part, making it fantastic for generating text piece by piece. The heart of this design is something called self-attention. It allows the model to really understand how important each word in a sentence is when predicting what comes next. It's like giving the model context beyond just the immediately preceding words. And it's trained through two main stages. First, it learns general language by reading tons of text without any specific instructions, essentially learning to predict the next word. Then, you can tweak it for a particular job, like translation or question answering, but often prompt engineering is enough now. Okay, let's talk about autoregression. It's a really important piece of how models like GPT actually work. Think of it like predicting the next word in a sentence based solely on what you've already written. These models aren't smart in the way we are. They are incredibly sophisticated pattern matching machines that have learned from huge amounts of text data. They essentially calculate probabilities, how likely each possible word is to come next, given everything that came before it. It's a bit like a really complex autocomplete. The code example I'm showing is a super simplified illustration, but it gives you the general idea. Basically, they predict based on what they've already seen. Okay, let's dive into how DALL-E actually creates those amazing images. It's a really fascinating process. First, you give it your text prompt like a corgi riding a skateboard in space. The language model then transforms that sentence into a series of numbers, essentially a code representing the meaning behind your words. Next, another part of DALL-E creates an image blueprint based on those numbers. It's like generating a rough sketch. Then comes the really clever part, diffusion. DALL-E starts with pure noise and then slowly removes it, guided by that image blueprint. Think of it as sculpting an image from nothing. Finally, it refines the image and makes it bigger, ready to be shared. Pretty cool, huh? Okay, let's talk about Clip. It's a really clever piece of the puzzle in how DALL-E creates images. Think of Clip as a translator between words and pictures. It's trained on a huge number of images paired with their descriptions, so it's learned to understand what things look like when they are described in text. When you give DALL-E a prompt, like a corgi riding a skateboard, Clip turns that into a numerical code and embedding representing the meaning of your request. Then, DALL-E uses this code as a guide to generate an image that matches that meaning. It's really cool how it allows DALL-E to get what you're trying to visualize. Okay, so let's talk about the brains behind stable diffusion, latent diffusion models. Basically, instead of directly editing pixels like some other image generators, these models work in a clever shortcut called a latent space. Imagine taking an image and slowly adding noise until it's just pure static. Then, the LDM learns how to reverse this process, starting from that random noise and carefully removing it step by step, reconstructing a beautiful image. The real key is operating in this compressed latent space, which makes the whole thing much faster and less resource intensive than working directly with pixels. Okay, let's dive into how stable diffusion actually creates images. It all starts with something called the denoising autoencoder, or D. Basically, it's like teaching an AI to clean up noisy pictures. First, the image you want goes through an encoder which squashes it down into a smaller, more abstract version of itself, living in what we call latent space. Then random noise gets added to that compressed representation. It's transformed into pure static. Finally, a decoder comes along and tries to remove all that noise, reconstructing the original image. This process is repeated many times, gradually refining the details until you get something really impressive. Stable Diffusion uses two main DAE and encoder-decoder pair to handle the big picture and a variational autoencoder for smoother transitions between the pixel world and this latent space. Okay, let's dive into VAE. They're a really clever technique in generative AI. Unlike regular autoencoders that just create a single snapshot of your data, a VAE learns to represent the entire distribution of the data. It's like building a map instead of just a single point. You have an encoder which squashes everything down into a lower dimensional space, but crucially, it doesn't output a single point, it outputs a probability, usually described by a Gaussian curve. Then you have a decoder that takes this probabilistic representation and rebuilds the data from it, creating something new and related to what it was trained on. This allows us to generate entirely new images, text, or even create smooth transitions between different pieces of data, like morphing a cat into a dog. Okay, let's talk about UNets. They're really important in how some of these advanced AI image generators like Stable Diffusion actually create pictures. Think of them as a clever combination of an encoder and a decoder. The encoder squashes down the initial image, extracting its key features while reducing its size. Then, the decoder takes those features and painstakingly rebuilds the image back up to full resolution. But here's the magic. UNets have skip connections that link the encoder's information directly to the decoder at corresponding scales. This ensures the network doesn't lose any crucial details during the compression process. That remembers exactly what's important. And in models like Stable Diffusion, UNets predict the noise added to a picture as part of a diffusion process, allowing them to reconstruct an image from pure random noise based on your text prompt. Okay, let's talk about classifier-free guidance, or CFG. It's a clever way to fine-tune diffusion models like Stable Diffusion. Think of it this way: traditionally, these models had a separate classifier that told them how much noise to take away at each step based on the prompt you give it. But CFG does away with that extra piece and uses the model's existing knowledge from its training data. It's trained to predict the noise added to an image with a text prompt, and then without *1. Then, during generation, we feed the model the text prompt plus a conditioning signal, which is basically our request for a specific image. We can control how strongly this request influences the output by adjusting something called the CFG scale. Higher values make it more insistent on following the prompt, while lower values give it more creative leeway. Okay, let's talk about how the way you phrase your requests those prompts completely impacts what these AI models come up with. Think of it like giving instructions to a really talented but slightly literal assistant. The more specific and detailed your instructions are, the better the results will be. We're talking about things like being super clear about exactly what you want, perhaps even assigning a role to the AI you're a travel writer, and setting rules or constraints on the output. Finally, giving examples of what you're looking for can really help the model understand your vision. It's all about experimenting and refining your prompts until you get exactly what you need. Okay, let's talk about fine-tuning. These huge generative models like ChatGPT are amazing at general tasks, but they're really good at being ***. It's kind of like giving them a massive general education. They know a lot, but not everything. Fine-tuning is where we take those already smart models and give them specialized training on a smaller data set. Imagine you're teaching someone who already knows a little bit about something. You don't have to explain the basics again, you can just focus on the specific details. We provide a smaller, focused data set, then train the model, further adjusting its internal settings to become an expert in that particular area. It's a fantastic way to get really powerful and targeted AI for your projects. Okay, so let's talk about how we actually make these massive language models like ChatGPT really good. Initially, they just predict the next word in a sentence, which is powerful, but can lead to some pretty weird or even wrong answers. The key is something called reinforcement learning from human feedback, or RLHF. It's a three-step process. First, we train the model on examples of what humans actually write and expect. Then, we get humans to rate different outputs, basically saying which ones are better. This creates a reward model that learns what good answers look like. Finally, we use reinforcement learning, where the model gets rewarded for generating outputs that score well with this reward model, much like training a dog. It's all about aligning the model's behavior with what humans truly want. Okay, so let's talk about how we get AI to create pictures from words. It's a pretty incredible feat. Basically, these systems learn the connection between language and visual concepts. They start by turning your text prompt like a fluffy pink dragon flying over a rainbow into numbers that represent its meaning. Then, using something called a diffusion model, they gradually transform random noise into an image that matches that description. It's like taking a blank canvas and sculpting it step by step based on what you told the AI to create. Okay, let's talk about how GAN and diffusion models stack up when it comes to creating images. GAN are like a game between two networks, one trying to create realistic pictures and the other trying to spot fakes. They are pretty fast at generating images once trained, but things can get tricky with training stability, and they sometimes struggle to produce lots of different variations. Diffusion models, on the other hand, work by gradually adding noise to an image until it's completely random, then learning how to take that noise back down to a recognizable picture. They're more stable to train, give you much better diversity in your results, and tend to generate images with higher overall quality, although they are slower to create new images. Okay, let's talk about how tokenization plays a crucial role in how large language models actually work. LLM don't read text the way we do, they operate on numbers. Tokenization is the key process of breaking down that text, whether it's words or parts of words, into these numerical tokens. Different methods like word-based, subword-based techniques such as BPE, and character-based approaches exist. The size of your vocabulary, how many different tokens a model knows, directly impacts how quickly the model trains and performs during inference. Furthermore, the length of each token limits the amount of context the model can consider at once, which is important for understanding longer pieces of text. And finally, how these tokens are converted into numerical embeddings also has a big impact on how well the model understands relationships between words. It's like having the right set of building blocks to construct meaning. Okay, let's talk about LoRA. It's a really smart way to customize those massive generative AI models like GPT without needing massive computing resources. Think of the base model as a super smart expert who already knows a lot. LoRA allows you to teach that expert a specific skill or style with a tiny fraction of the effort. It does this by adding small, adjustable parts, almost like little tweaks, directly into certain layers of the original model, and it's way more efficient than retraining the whole thing. Okay, let's talk about embeddings. They're a really important concept when we're diving into advanced generative AI like GPT and Stable Diffusion. Basically, these models don't just see words or pixels as random things. They need to understand what those words mean or what those pixels represent . Embeddings are the way they do that. They're numerical representations of data, so for example, a word gets turned into a set of numbers. Words with similar meanings end up being close together in this number space, allowing the AI to recognize relationships and generate relevant content. It's like giving them a secret language to understand everything. Okay, let's talk about a really cool concept called latent space manipulation. These AI model things like Stable Diffusion and DALL-E aren't just randomly generating images or text. They are actually operating in this hidden world, what we call the latent space. It's essentially a super compressed version of everything they've learned from their training data. Instead of working directly with pixels or words, we're adjusting controls that describe the desired outcome. It's like having sliders for style, composition. You can really fine-tune things. We first encode our input into this space, then tweak those points, and finally decode it back to a final result. Okay, let's talk about how we can make generative AI even more powerful using something called transfer learning. Think of it like this: instead of starting from zero every single time we want a model to do something new, we give it a boost by building on what it already knows. Specifically with models like GPT and Stable Diffusion, they've been trained on massive amounts of data, text or images, respectively. So, transfer learning means taking those existing brains, adjust them slightly using our own smaller data set, and bam, we get better results faster than if we were training from scratch. Okay, let's talk about what makes scaling these amazing generative AI models so tricky. It's a lot more than just buying faster computers. The biggest hurdle is the sheer cost of training and running them. We're talking massive investments in GPU time and memory. Then there's the data. You need tons of it, which can be hard to find, clean up, and keep high quality. Serving these models quickly for real-time use also presents a big challenge. We call that latency. And, honestly, as the model gets bigger, so does its memory footprint, making deployment complicated. Finally, scaling just amplifies any biases already present in the data, so it's really important to be aware of those and actively work to address them. Okay, let's talk about how Stable Diffusion manages to create such stunningly detailed images even on relatively modest computers. It's a clever bit of engineering. The key is this thing called latent diffusion models, LDMs. Instead of working directly with the raw pixels of an image, which would be incredibly demanding, Stable Diffusion first compresses those pixels into a low-dimensional latent representation using something called a variational autoencoder. It's like creating a super efficient summary of the image. Then, it performs its diffusion process, slowly removing noise in that latent space, guided by your text prompt. And because most of this processing happens in this compressed form, it doesn't require as much computing power or memory as if you were working directly with high-resolution pixels. Plus, techniques like model distillation and attention mechanisms really help to optimize the process. Basically, Stable Diffusion is a master of efficiency. Okay, let's talk about making these massive language models actually usable, not just running them in research labs. The biggest challenge is getting them to respond quickly, and that's where inference optimization comes in. It's all about speeding things up without sacrificing too much quality. We have a few key strategies. First, quantization, essentially shrinking the numbers representing our model's weights, like going from 32-bit precision to 8-bit. This makes everything run faster and uses less memory. Then there's pruning, which is like trimming the fat out of the model by removing connections that aren't really important. Another approach is knowledge distillation, where we train a smaller, simpler model to copy the behavior of a larger one. Finally, for truly gigantic models, we can split them across multiple GPU using techniques like model-intensive parallelism. You'll see a simple example in PyTorch showing how to quantize a model. It's a really common starting point. Okay, let's talk about something really exciting: multimodal AI. Basically, instead of just generating one thing at a time, like just pictures from words, these new systems can understand and combine information from multiple sources. DALL-E 3 is a fantastic illustration of this. It's not just taking your text prompt and creating an image, it actually uses images as part of the instruction. It's learned how different things in the world connect together, making it capable of some truly impressive creative outputs. Okay, let's talk about how we can make these massive generative AI models more manageable. We're looking at two key techniques: quantization and pruning. Think of quantization as simplifying the language the model uses. Instead of using a lot of detailed information like 32-bit numbers, we reduce it to a simpler form, like 8-bit or even less. This makes the model smaller and faster, but you need to be careful not to lose too much detail along the way. Now, pruning is like trimming away unnecessary branches from a tree. We identify parts of the model that aren't contributing much to the final output and just remove them. It creates a leaner, more efficient model without drastically impacting its ability to generate amazing results. Okay, let's talk about what really makes these generative AI models tick. The key player here is the transformer architecture. Forget how older systems process things one step at a time. Transformers use something called self-attention. This allows each part of the data, like a word in a sentence or a pixel in an image, to consider all other parts and figure out what's most relevant to it. It's like they're constantly asking, what does this relate to? And then using that information to create something new, whether it's text or an image. Okay, so GPT models aren't just pulling words out of thin air. They're actually predicting what comes next, one token at a time, which is basically a word or part of a word. To make sure that the generated text makes sense and isn't *to* random, we use something called token sampling. There are a few ways to do this. Temperature controls how adventurous the model gets. Higher numbers mean more surprising results, while lower ones keep things pretty predictable. Top K focuses on just the most likely options. It cuts down on weirdness. And then there's Top P, which dynamically picks a group of tokens that add up to a certain probability threshold. Basically, you can tweak these settings to get exactly the kind of text you're looking for. It's all about finding the right balance. Okay, so as we're looking at generative AI, it's really important to think about how we use these powerful tools responsibly. There are some big safety concerns, things like the potential for spreading misinformation and generating harmful content. We also need to be mindful of privacy risks and consider the impact on jobs. But thankfully, there are ways we can tackle bias. That means actively working to make sure our training data is diverse, using tools to spot bias in the models themselves, and even retraining them with feedback from humans. Prompt engineering, how we ask the AI questions, plays a huge role too. It's all about building these systems ethically. Okay, so Stable Diffusion is amazing at creating images from text prompts, but sometimes it can be a little unpredictable. That's where ControlNet comes in. It's like giving Stable Diffusion extra instructions. Think of it as a set of guiding rails. ControlNet adds these conditional input layers, things like edge maps which highlight the outlines of objects, segmentation masks showing different areas of an image, or even pose estimations to help steer the generation process. Basically, you're not just telling it what * to draw, but also * how * to draw it. It really helps reduce randomness and makes the results much more consistent. Okay, let's talk about prompt interpolation. It's a really neat trick we can use with tools like Stable Diffusion to create smooth transitions between images based on text prompts. Think of it as blending two ideas together, step by step. Instead of just jumping from one concept to the next, you get a series of images that gradually evolve and combine those features. It's essentially creating an animation of your prompt, which can lead to some really interesting and unexpected results. The AI treats the prompts like points in a huge space, and it calculates where the in-between points would be for a smooth transition. Okay, let's dive into textual inversion. It's a really clever way to tweak generative AI models like Stable Diffusion. Think of it as teaching the model something new without needing a massive overhaul. You start with an image or a concept you want to see repeated in future generations. Then, through lots of prompting and generation, which can be a bit messy at first, the model learns a tiny textual code representing that concept. You can then add this code to your prompts, like a red apple wearing sunglasses, and the AI will generate images reflecting that specific style or object. Okay, so let's talk about how Stable Diffusion actually creates those amazing images. The magic isn't just in the unit itself, it's really about a carefully designed pipeline. Think of it like an assembly line for creating visuals. First, we start with an image, any image. Then, we add random noise to it until it looks like pure static. The unit is then trained to take that noisy image and intelligently remove the noise, guided by your text prompt. It's a clever process. And importantly, Stable Diffusion uses a text encoder, like Clip, to understand what you're asking for in words and translate that into numbers the unit can work with. Finally, a VAE helps us compress and decompress images efficiently so we can work within this latent space. Okay, let's talk about Dream Booth. It's a really cool technique for getting Stable Diffusion to create images of things you care about, like your pets or family photos. Basically, it's all about personalization. You don't need hundreds of pictures, just 3-5 will do. The model learns what your specific subject looks like and then uses that knowledge to generate totally custom images based on prompts. Okay, let's talk about a really clever trick called negative prompting. It's like giving your AI art generator a set of instructions on what not to do. Basically, you tell it don't include this, and it will try its best to avoid it. It's especially useful for cleaning up images, removing blurry parts, unwanted people, or any distracting text. It's all about refining the output by directing the AI away from things you don't want. Okay, so these generative AI models are incredibly powerful, but they are not something you can just run directly from your computer. That's where API come in. The OpenAI API is probably the most well-known. It gives you access to their amazing language and image generation models like GPT and DALL-E. It's a simple REST interface. You send a prompt, and the model responds. Then there's Hugging Face Inference API. They host thousands of pre-trained models that you can easily use through their API. And finally, Replicate is a fantastic service that simplifies deploying and running different AI models, like Stable Diffusion, making it super easy to get started. Okay, so generative AI models like ChatGPT are brilliant at creating new stuff, but sometimes they need a little help to find the right information. That's where embeddings come in. Essentially, we turn words and documents into numerical codes. Think of them as coordinates in a giant space. The closer two concepts are in the space, the more similar they are. We use these embeddings to build indexes for our data, so when someone asks a question, we can quickly find the most relevant information by comparing the question's embedding with all the document embeddings. It's like a super smart search engine that understands meaning instead of just matching keywords. Okay, so let's talk about image-to-image generation. It's a really cool technique that uses diffusion models to change an existing picture into something new. Instead of starting with nothing like random noise, we begin with an initial image. The model then learns how to slowly remove the added noise while being guided by another image, kind of like sculpting. You start with a rough block and refine it step by step until you get the desired result. Okay, let's talk about how we actually control generative AI. It's not just asking for an image, it's understanding that these models work in a hidden space called latent space. Think of it like a highly compressed version of the final picture. The really cool part is that we can do math on those compressed representations, simple things like adding, subtracting, or scaling vectors. Adding one vector to another might combine two different concepts, so you could add beach to mountain and suddenly have a mountain beach. Subtracting can remove elements, and scaling lets us boost or diminish the influence of particular features. It's like having a digital paintbrush that responds to mathematical commands. Okay, let's dive into something really fascinating: attention mechanisms. These are absolutely vital to understanding how powerful models like GPT and DALL-E actually work. Think of it like this: when you read a sentence, you don't just look at every word with equal intensity, you focus on the most important ones. Attention mechanisms do exactly that for AI. They help these huge models weigh the relevance of different parts of their input, whether it's text or images, to generate better outputs. Specifically, self-attention lets the model understand how different pieces within the same asterisk input relate to each other, and cross-attention helps combine information from multiple sources. Basically, attention is what allows these models to capture complex relationships and produce far more coherent results. Okay, let's talk about how we make these massive language models, like ChatGPT, actually good at what they do. It's not just about feeding them tons of text. That's the first step. Then, we use something called RLHF, reinforcement learning from human feedback. Basically, we start by training the model on examples of how it should respond. Think of it like showing it a bunch of good answers. Next, we get humans to rate different responses to the same question, telling us which ones were helpful, accurate, and harmless. This data is then used to train an AI that can predict how good a response will be. Finally, we use reinforcement learning, specifically PPO, to fine-tune the original model, using the reward model as its guide. It's like teaching the model what good looks like through direct human feedback, leading to much more helpful and aligned conversations. Okay, let's talk about how we can really shape the output from our generative AI models. Instead of just picking the most likely word or pixel at each step, which often leads to a bit of repetition or weirdness, there are some clever sampling techniques we can use. Think of temperature as controlling the level of randomness. Higher values give you more creative, but potentially less coherent results. Top K and nucleus sampling are ways to narrow down the possibilities, focusing on the most relevant choices. And when it comes to image generation, methods like DDIM and classifier-free guidance allow us to really steer the output towards a particular style or concept even without explicitly training separate classifiers for each one. They are all about making the process more efficient and giving us finer control. Let's talk about model distillation. Basically, it's a way to shrink down really big AI models without losing all their smarts. Think of a giant expert the teacher model giving lessons to a smaller student model. The student learns by watching the teacher and trying to imitate its thinking process, not just by being told what's right or wrong. This is particularly useful in generative AI like Stable Diffusion, where we want super fast image generation, and distillation helps us get there. Okay, let's dive into how AI can now create video. Models like Runway Geminis 2 and Pika Labs are really pushing the boundaries of what's possible. Runway uses a technique called diffusion. It starts with pure noise and slowly builds up an image based on your text description frame by frame. It's like watching a picture gradually come to life. Pika Labs is a bit different. It focuses on generating just a few keyframes, the most important moments in the video, and then uses motion vectors to smoothly fill in all the frames in between. Think of it like creating an animation storyboard, but the AI does the work of drawing each frame. Both rely heavily on powerful neural networks trained on huge datasets. Okay, let's talk about how we manage these massive generative AI models. One crucial technique is called checkpointing. Basically, it's like taking a save point of your model's progress during training. Without checkpoints, if you lose power or have an interruption, you'd have to start all over again. Then there's merging. Think about combining the knowledge from multiple models trained on different data. This can make the final model really powerful and adaptable. But it's not as simple as just slapping them together. Careful consideration needs to be given to how those weights are combined, which directly impacts the quality and consistency of the outputs you get. More checkpoints mean more frequent saves, but also more storage. And when merging, different strategies can dramatically shift what the model produces, so it's important to experiment and understand how these techniques shape the distribution of your AI output. Okay, let's talk about how these open source generative AI models are changing the game for businesses. Basically, we're seeing a huge shift away from being locked into specific providers like OpenAI or Midjourney. Because models like Llama 2 and Stable Diffusion are available openly, companies can build their own custom AI solutions without relying on those big platforms. This means lower costs in the long run because you aren't paying for every single API call. But it's not all sunshine and roses. You need to have strong security practices when working with these models and ensure your data is protected. Plus, the open source community is really driving innovation, so there's a lot of excitement around what's possible. Okay, let's talk about a really clever technique called progressive growing in GN. Basically, traditional GN can have trouble creating high-quality images, especially when you're trying to get super detailed results. Progressive growing is like building an image step by step. The GN starts by learning how to create small, simple pictures, maybe just forks for pixels. Then, as it trains, it gradually adds more detail and increases the size of the images. It's almost like sculpting, starting with a rough block and slowly refining it into something amazing. This approach helps stabilize training, speeds up the process, and ultimately leads to much better image quality overall. Okay, let's talk about how these AI models understand what we want to see when we give them a description. Both DALL-E and Stable Diffusion start by turning your words into numbers, basically a secret code the computer can use. Stable Diffusion uses something called a diffusion process, where it starts with random noise and slowly removes it until you have an image that matches your prompt. It's like taking a blank canvas and gradually adding details. DALL-E works in a slightly different way, using a latent space to make the whole thing more efficient. And both models keep refining their images over and over again based on what they've already created. DALL-E is great for making changes to existing pictures, while Stable Diffusion lets you really pick and choose exactly which parts of an image you want to edit with new text prompts. It's fantastic for localized adjustments. Okay, so generative AI models are powerful but sometimes feel like black boxes. That's where attention maps come in. They're a way to take a peek inside and see what the model was actually paying attention to when it created something, whether that's text or an image. Essentially, they highlight which parts of your input were most important for generating the output. In text models like GPT, they show you which words in your prompt were driving the prediction of the next word. And with image generators like Stable Diffusion, they illuminate the key elements you asked it to focus on. It's a really valuable tool for understanding how these complex systems work and potentially improving their performance. Okay, let's talk about how foundation models are really revolutionizing AI. Think of these massive models like GPT-4 or DALL-E 2 as incredibly versatile learning machines. They've been fed tons of data from all sorts of sources: text, images, audio, video, you name it. The cool thing is, they don't just learn to do one specific task, they learn a general understanding of how information relates across different formats. So, instead of building separate AI for generating images from descriptions or translating speech to text, foundation models can essentially bridge the gap and create these combined outputs. They do this by finding common patterns and relationships in all of that data, aligning different modalities, and even exhibiting surprising new capabilities as they get bigger. Ready to see some examples? Okay, let's talk about cascading diffusion. It's a really clever way of boosting image generation quality. Imagine traditional diffusion models like starting with an image and slowly adding noise until you get pure static. Then the AI learns to reverse that process. Cascading diffusion takes this idea even further. Instead of one big model doing everything, it uses a series of specialized diffusion models working together in stages. The first stage builds the overall structure, the main objects, and layout. The next ones refine those details, adding textures, colors, and lighting. And finally, very small details like edges and patterns are perfected. This approach leads to more detailed images, gives us more control over the process, and reduces common problems like blurriness. Okay, let's talk about scaling these amazing diffusion models like Stable Diffusion. The really tricky part is that they're huge. We're talking about models with billions of parameters, which means a massive amount of memory, often 80 gigabytes or more just to run them. And it's not just about memory. The math involved in generating an image is incredibly complex and requires a ton of processing power. Consumer graphics cards are great for gaming, but they don't have the speed needed to generate images quickly. Because of this, we often see slow generation times when trying to run these models locally. Fortunately, researchers are working on techniques like shrinking the model size and distributing the workload across multiple machines or GPU, but that adds a layer of complexity. Okay, so when you're working with really big generative AI models, training them can take really long time. That's where distributed training comes in. We'll be talking about multi-worker mirrored strategy. It's a clever way to get around that. Basically, it takes your data and divides it up equally among multiple workers, usually GPU. Each worker then trains a bit of the model independently. Because they all have roughly the same amount of work, there's less need for them to constantly talk to each other, making training faster. It's handled automatically by PyTorch Lightning, so you don't need to worry about complex synchronization. Just set multi-worker mirrored strategy in your trainer and let it do its thing. You can easily experiment with different numbers of workers and see how that impacts the time it takes to train your model. Okay, so when we're scaling up generative AI training across many GPU, there are different ways to handle the model and its parameters. Mirrored strategy is pretty straightforward. It just copies the entire thing onto each GPU. That's easy to set up, but it means every GPU has to constantly talk to the others to share gradients, which can become a major bottleneck as models get bigger. Then there's parameter server strategy. Instead of copying everything, each GPU only holds its gradients. All the parameters and optimizer states live on a central server. After each gradient update, the GPUs send their updates to the server, which then applies them. This drastically reduces communication overhead, making it much better for really large models or when you have a lot of GPU but limited bandwidth between them. So, parameter server strategy is generally your go-to choice if you're dealing with massive models and a high number of GPU. Okay, let's talk about how TensorFlow serving helps us manage different versions of our AI models. It's incredibly smart about this. It automatically keeps track of every single version that gets deployed, using things like Git hashes to uniquely identify them. This means we have a complete history. Now for /B testing, think of it as letting two different model versions compete to see which one performs best with real users. TensorFlow serving lets you split your traffic and measure key metrics like accuracy and latency to make data-driven decisions about which version to use for everyone. It's really powerful for optimizing performance. Okay, so let's talk about something really helpful when working with generative AI, TensorFlow metadata or TF&D. Basically, it's like a detailed report card for your dataset. It doesn't contain the data itself, but it describes incredibly well. It tracks where the data came from, how it was cleaned up and modified, and even provides statistics to help you spot any weirdness or inconsistencies. This is super important because without this information, you're making assumptions about your data that could lead to unexpected results in your generative models. It's like having a built-in validation system directly within TensorFlow, ensuring everything aligns before it gets fed into the model. Okay, let's talk about how TensorFlow Transform or TFT plays a critical role in getting your generative AI models ready for production. Basically, TFT is like a super efficient data chef, handling all the complex transformations you need to do before feeding your data into the model. It's not just about simple changes, it's about creating a consistent and structured dataset that each of those models can understand. We define what we want to do using recipes, which are essentially Python functions. Then TFT takes these recipes and applies them automatically to your data, creating a TensorFlow dataset that is optimized for speed and efficiency. Okay, let's talk about getting your TensorFlow models live on Kubernetes. It's a great way to scale them up. First, you'll package your model along with all the necessary libraries into a Docker container. Think of it like a little box that contains everything your model needs. Then, you write a configuration file for Kubernetes, basically telling it how many copies of your model to run and how much memory and processing power each one should have. We'll set up health checks too so Kubernetes knows if things are running smoothly. Finally, we create a service to make the model accessible through an endpoint. And don't forget about scaling. Kubernetes can automatically add or remove replicas as needed based on demand, and monitoring helps you keep an eye on everything. Okay, let's talk about keeping your TensorFlow serving endpoint safe when they're out in the real world. Think of them as valuable assets. They need protection. The biggest risk is attackers trying to get unauthorized access. We want to make sure only trusted clients can connect and that they only have access to what they are allowed. We'll use things like strong authentication, so we know who is asking for something, and authorization, so we know what they're allowed to do. Encryption TLS 1.2 or higher is absolutely essential. It scrambles the data while it's traveling. Rate limiting helps stop attackers from overwhelming your service with too many requests. And finally, always check and clean up any user input to prevent problems. Okay, let's talk about building a robust machine learning pipeline with TFX TensorFlow Extended. First, you start by defining your entire process, breaking it down into logical stages like data validation and training. Then, you configure the specific components that make up each stage, things like your trainer or feature engineer. Next, you tell TFX where your data lives and where the final model will go. The magic happens when you define a complete pipeline using a YAML file. This directs everything. And finally, don't forget to monitor performance and set up feedback loops so your models keep getting better over time. Okay, let's talk about TFX example gen. It's a really handy component for building generative AI pipelines. Basically, it helps you get your data ready by intelligently augmenting it. Imagine you have a dataset with some rare events, and your model isn't performing well on them. That's where example gen shines. It figures out which existing examples are similar to those rare events and then generates new examples that look like they belong there too. Think of it as creating realistic duplicates to give your model more practice recognizing what it needs to learn. It does this by first profiling the data, finding similar examples, and then building synthetic versions of them, adding more data without having to manually collect everything yourself. Okay, let's talk about TensorFlow Model Analysis, or TFMA. It's a really powerful tool for digging deeper into the models we use in generative AI like GPT and DALL-E. Basically, it helps us understand why a model is making the choices it does after it's been trained. TFMA works by collecting data from the outputs of your model. Think of it as taking snapshots of what the model produces. Then, it profiles that data to see which inputs are most common and influential. Finally, it calculates metrics like how confident the model is in its answers, whether they're novel or diverse, and if they align with what you'd expect. The result: detailed reports that give you actionable insights into your model's strengths and weaknesses, going far beyond just simple accuracy scores. Okay, let's talk about the TFX Evaluator. It's like a quality control system for your generative AI models. Think of it as going beyond just training. You need to measure how good your model actually is at what it does. The TFX Evaluator helps you do that systematically by letting you define specific metrics, compare against reference data, and even get human feedback if needed. It's a vital part of the TFX platform for ensuring your generative AI models are producing high-quality results, not just technically sound, but also genuinely good. Okay, so let's talk about schema inference in TensorFlow. It's a really clever feature for data validation. Basically, instead of you having to painstakingly define every single column type in your dataset as integer, float, or string, TensorFlow can figure that out for u. It analyzes the data itself using techniques like looking at histograms and summary statistics to understand how each feature is distributed. Then it assigns the best possible data type, saying float 32, in 32, etc., minimizing any potential issues with your model's training. This saves a ton of manual effort, especially when dealing with datasets that aren't perfectly clean or have unexpected variations in their values. And often, using TensorFlow's inferred schema can actually lead to a better performing model. Okay, so we've got some really impressive generative AI models out there: GPT for text, DALL-E for images, Stable Diffusion too. But a lot of times they're like black boxes. We know what they produce, but not always why. That's where explainable AI, or XI, comes in. TensorFlow gives us some really powerful tools to start figuring out how these models are making their decisions. We're talking about techniques like SHAP and line that can show us which parts of a prompt, whether it's text for GPT or details in an image for DALL-E, are most influential on the output. It's all about understanding these feature contributions, visualizing them with TensorBoard, and ultimately building more trustworthy and understandable AI systems. Okay, let's talk about integrated gradients, a really clever way to understand how generative AI models like GPT and Stable Diffusion arrive at their outputs. The main challenge is that as these networks get deeper and more complex, traditional methods of figuring out which inputs are most important struggle because the gradients shrink dramatically. Integrated gradients tackles this by essentially calculating an integral of the gradient along a path from a simple baseline like all zeros towards your actual input. Think of it like adding up the influence of each feature as you get closer to the final result. It's a powerful tool for explainability and helps us understand why these models are making the decisions they do. Okay, so when we're dealing with really big TensorFlow models, especially those used to generate things like images or text, it's super important to keep an eye on how they're using memory and how fast they're running. Sometimes these models can develop problems where they slowly eat up more and more memory, leading to slowdowns or even crashes. We want to find the cause of those issues. Common problems include memory leaks where things aren't being properly released, bottlenecks in the model itself, like slow calculations, or even just a really sluggish way of getting data into the model. To tackle these, we use tools like TensorBoard Profiler, which lets us see exactly what's happening with memory and performance, and also TF Profiler for deeper dives. And you can manually track memory usage in your code too. The key is to regularly monitor your model and profile it. That'll help you find and fix those bottlenecks before they cause big problems. Okay, let's talk about how we make these massive AI models run smoothly on our phones. TensorFlow Lite delegates are essentially translators. They bridge the gap between the standard TensorFlow Lite interpreter and the specific hardware capabilities of your device. Think of it like this: a giant model needs to do a lot of heavy lifting, but a phone has limited power. These delegates take those complex calculations and rewrite them in a way that's super efficient for your phone's GPU or other specialized processors. It results in a much faster experience, often 2 to 10 times quicker. And because they're using the device's hardware, it also uses less battery. Let's talk about bringing AI closer to where we need it, at the edge. That's where the Edge GPU comes in. It's a specialized hardware chip from Google, basically like a mini supercomputer designed to quickly and efficiently run machine learning models on devices that don't have massive processing power, like your phone or even small robots. It's incredibly good at making predictions, what we call inference, using those trained models, all while using very little power. Because of this hardware acceleration, it delivers faster response times and extends battery life. The process of deploying a TensorFlow Lite model involves a few steps. First, you convert your model to the TensorFlow Lite format, then you can optionally quantize it for even better performance. Finally, you use a tool to compile that optimized model specifically for the Edge GPU, and then deploy it to an Edge GPU-enabled device. Okay, let's talk about bringing those impressive TensorFlow models you've built into your web applications. The key here is TensorFlow JS. It allows you to run these models directly in the browser. To do that, we need to convert our existing save model. We use a tool called TensorFlow Converter, which is a command line utility. You essentially point it at where your saved model is located and tell it where to create the JavaScript bundle. And don't forget, you'll also need to include the TensorFlow JS library in your HTML so that everything can load correctly. Okay, let's dive into some of the tricky stuff when you're trying to get TensorFlow-powered generative AI running smoothly in real time. It's not just about building a cool model, it's about making sure it responds quickly. One of the biggest issues is the sheer amount of computing power needed. These models can be really demanding on your hardware. Then there's memory, because you need to feed data to the model constantly and access that data super fast. Batching processing multiple inputs at once can help with speed, but it also adds a little bit of delay. And frankly, relying only on a regular computer processor just won't cut it. You often need powerful graphics cards or specialized hardware like TPU to keep up. Finally, we have to be smart about how the model itself is built, and optimized techniques like reducing the precision of the numbers used in calculations can really help make things run faster. Okay, let's talk about how to keep your generative AI models performing well over time. You'll often see model drift. Essentially, the data they were trained on changes, and their outputs start to degrade. TensorFlow pipelines are a really powerful tool for tackling this. We start with monitoring the data itself, tracking things like the types of words being used or the pixels in images. Then, we set up triggers so when the data shifts significantly, it automatically kicks off a retraining process. We can use TensorFlow's TF function to build reusable training routines and schedule them to run regularly. It's all about proactive monitoring and retraining. Don't wait until your model is completely useless. Okay, let's talk about feature stores. Think of them as a central hub for all the data you need to feed into your TensorFlow models. They're like a really organized database specifically designed for machine learning features. So, what exactly is a feature store? It's basically a place where you keep all your prepared data, things like user ID, product categories, or whatever information helps your model learn. The great thing about it is that it separates the process of creating those features from actually using them in your model. This means TensorFlow can pull features directly from this store during training and, even more importantly, consistently deliver those same features to your deployed models when they're running in real time. This helps avoid issues like data drift, where a model suddenly starts performing poorly because the input data changes unexpectedly. It's all about making your AI systems more reliable and efficient. Okay, let's talk about assembling TensorFlow models. It's a really clever way to make your AI systems even better. Basically, instead of relying on just one model, we combine the predictions of several different ones. This often results in a huge boost in accuracy and makes them more reliable because they are less likely to be fooled by weird data points. However, there's a catch. It takes a lot more computing power to run multiple models at once, and setting up the ensemble can get complicated. But tools like weighted averaging and stacking can help manage that complexity. Think of it as a team effort where each model specializes in something different, and together they're stronger. Okay, let's talk about handling multi-label classification when you have a really skewed dataset where some labels are much more common than others. This is a frequent problem with image recognition, natural language processing, and many other areas. TensorFlow offers several strategies to tackle this. First up, class weights. These give extra importance to the less frequent classes during training, making sure they don't get completely ignored. Next, we're sampling techniques like smooth, which creates synthetic data for minority labels, or undersampling the majority ones. Finally, you can adjust your loss function using cost-sensitive learning, putting more penalty on misclassifications of those harder to get labels. The code snippet shows a quick example of how you might use Smote within Blend library. Okay, let's talk about how TensorFlow makes the most of all the different types of hardware we have available for AI. It's called mixed device placement, and it's a really clever way to get your models running smoothly. Basically, TensorFlow figures out which parts of a model are best suited for each device, whether that's your regular CPU, a powerful GPU, or even a TPU. It does this automatically by default, choosing the fastest option it can find. But you can also take control and tell TensorFlow exactly where to put things if you know what you're doing. It uses something called TF device to specify which device each part of your model should run on. And just as important, data needs to be on the same device as the operations that use it. TensorFlow will automatically manage moving data around for you. Okay, let's talk about how TensorFlow makes its models run really fast. It does this through two clever systems, tracing and caching. First, when you define a model, TensorFlow doesn't know exactly how it will be used until you actually start running it with some sample data. Tracing is like watching the model as it runs. It records the exact steps involved in calculating the results. This creates a static graph that represents all those operations. Then TensorFlow takes this graph and saves it caches it. So, when you want to use your model again, instead of retracing everything from scratch, it just loads the previously created graph and executes it directly. This significantly speeds things up, reduces memory usage, and allows for some really powerful optimizations. Okay, let's talk about a really important piece of the puzzle when training massive AI models in a distributed setting: that's checkpointing and recovery. Training these models across multiple GPUs is powerful, but it's also incredibly complex. It's like running a huge race with lots of runners. If someone trips, you don't want to lose all their progress. Checkpointing is basically taking regular snapshots of your model's weights, its brain, and where it's at in the learning process. We need this because things can go wrong: hardware failures, software bugs, or even a worker process just crashing. The system saves the state so you can restart from that point, saving an asterisk of wasted effort. It's like hitting save game on your favorite video game. We save at intervals, and then, if something goes sideways, we reload from the last checkpoint to keep training smoothly. There are some important things to consider when setting up the system. How often do you check? What's your storage strategy? And where will those checkpoints live? Okay, so when you're diving into generative AI and want to really get hands-on with training models locally, simulating distributed training can be a lifesaver. Instead of needing a huge cloud setup, we have some clever techniques. One approach is the parameter server architecture. Think of it like a central brain holding all the model's knowledge, while smaller workers handle the actual learning. Another popular method is data parallelism, using tools like Corvad or PyTorch's DDP, which splits your dataset across multiple devices so each one can learn independently. And if your model is really big and won't fit on a single device, you can use multi-parallelism to break it up. The code snippet I just showed is a basic example using PyTorch DDP Remember to adjust the device ID. It's a fantastic way to prototype, experiment, and debug before moving to cloud-based training. Okay, so when we're talking about making these massive generative AI models run efficiently on edge devices or in production, quantization is key. There are two main approaches, CAT and PTQ. QAT is like teaching a model to handle low precision right from the start by simulating it during training. It's a bit more involved, you need to retrain the model, but it typically results in a much smaller drop in accuracy compared to post-training quantization. PTQ, however, just converts the existing model to lower precision after it's already been trained. That's easier to do, but often leads to a bigger performance hit. Think of it like this, QAT is proactive, while PTQ is reactive. Okay, let's talk about something really important in TensorFlow, how operations actually work. Basically, there are two main ways they can behave, stateful and stateless. Stateless operations are like a calculator. You give it numbers, it does the math, and then it forgets everything. They're super efficient for processing big amounts of data because they can be run all at once. Now, stateful operations are different. They remember what happened before. Think of it like an RNN model that needs to keep track of past information, like in a language model predicting the next word. So, while stateless is about independent calculations, stateful has a memory. That's the key difference to remember. Okay, let's talk about how RNN can actually handle sentences of different lengths. The standard RNN have a bit of a problem when you throw in text that isn't all the same size, like a really long sentence versus a short one. To tackle this, we use recursive neural networks. Think of it like breaking down complex structures into smaller, similar pieces. The core idea is to define a function that repeatedly applies itself to these parts until you reach the simplest elements like individual words. This recursion handles variable input lengths perfectly, making them ideal for processing natural language where sentences can be wildly different in size. Okay, let's talk about speeding up hyperparameter tuning in TensorFlow. Finding the best settings for your model can take really long time, so we need to be smart about it. There are a few key ways to do this. First, you can divide the possible combinations of hyperparameters into smaller chunks and evaluate them simultaneously using multiprocessing. Then there's the option of distributing parts of the model itself across multiple devices if your architecture supports it. And finally, leveraging TensorFlow datasets and distributed training to load data and run trials in parallel on different machines or GPU. Remember, the key is to make sure your tuning process isn't bottlenecked by a/o. That's where you'll see the biggest gains from parallelism. I've included a simple example of how you might use multiprocessing to evaluate hyperparameters across multiple processes. This illustrates the basic concept adapted to your specific needs. Okay, let's talk about TensorFlow Cloud. Think of it as Google Cloud's way of making training complex AI models, and the cloud much easier. It takes care of all the heavy lifting, setting up servers, scaling resources as you need them, and generally handling all the infrastructure headaches. It gives you a single place to manage your entire process from prepping your data all the way through to deploying your finished model, making it a really streamlined experience for teams. Okay, let's talk about speeding up TensorFlow models for when you actually use them. That's called inference. It's not enough to just train a model, we need it to run quickly and efficiently. Now, CPU and GPU are fundamentally different beasts. CPU are good at all sorts of general computing tasks, while GPU are built specifically for doing massive amounts of calculations simultaneously, exactly what AI needs. So, how do we get the most out of each one? Well, on the CPU side, we can use techniques like reducing the precision of our numbers, combining operations into single steps, and generally streamlining the model structure. Then, with GPU, we want to take advantage of those special tensor cores that accelerate matrix math, process multiple inputs at once through batching, and make sure we're not constantly moving data back and forth between the CPU and GPU because that's a major slowdown. Finally, it is important to profile your models to find bottlenecks. Experimentation is really key here. There's no one-size-fits-all answer. Okay, let's talk about a subtle but important distinction when diving into generative AI models like Stable Diffusion and GPT. We often hear about feature columns and feature preprocessing layers, and they sound similar, but they are actually quite different. Think of feature columns as the individual pieces of data, maybe the color values from an image or how words are represented as numbers. These directly feed into a model layer. Now, feature preprocessing layers are like dedicated preparation stations. They take that raw data and do things like normalize it, scale it, or even break it down into smaller components like tokenizing text. It's all about getting the data in the best possible shape for the model to learn from effectively. Okay, let's talk about gradient clipping, a really important technique in TensorFlow and other deep learning frameworks. Basically, when we train neural networks, we need to adjust the weights based on how big the gradients are. But sometimes those gradients get huge, like really big. This is called exploding gradients, and it can cause training to go haywire. It's unstable. Gradient clipping is a simple but incredibly effective solution. It's like putting a safety limit on how much a gradient can change during an update. If a gradient gets too big, it gets scaled down. This keeps things stable, helps the network learn faster, and even lets us use bigger batches of data. So, if you're working with deep models, gradient clipping is definitely worth knowing about. Okay, let's talk about how to really boost your model training with cyclical learning rates in TensorFlow. Essentially, we're not just sticking with a single, constant learning rate. Instead, the rate bounces around. This helps our models navigate tricky parts of their lost landscape and find better solutions. We start by picking a good base rate, then figuring out how many iterations each cycle should last. It's important to set a minimum and maximum for these rates, usually much lower than that initial base value. Finally, we use TensorFlow's optimizers like Adam or SGD and tell them to employ the cyclic scheduler. It's a clever way to guide the training process. Okay, let's talk about the TensorFlow Model Garden. It's a really handy resource for anyone working with generative AI using TensorFlow. Basically, it's like a huge library of pre-built models. Think of them as ready-made components you can just drop into your projects. Google has put together a collection of these models that are already trained and optimized, so you don't have to start from scratch and spend weeks training something yourself. You get everything from computer vision models to natural language processing ones. The beauty is it's constantly being updated by the community, making it a fantastic place to find solutions and learn new techniques. Okay, let's talk about how TensorFlow handles data that isn't filled out completely. We call it sparse data. Think of a recommendation system. Users might only interact with a tiny fraction of all the items available. Instead of storing every interaction, even if it's just no click, we use sparse tensors. These tensors only keep track of the active interactions, which saves a ton of memory and processing power. We can create them using TF. Sparse tensor, specifying indices where the non-zero values are located and the actual values themselves. And TensorFlow offers some handy functions like converting to dense tensors or gathering specific elements based on those indices, all designed for efficient sparse operations. Okay, let's talk about handling huge amounts of time series data in TensorFlow. It's a common challenge. The key is to think about scale from the start. We need strategies for dealing with massive volumes and the speed at which new data arrives. TensorFlow's distributed training options like mirrored strategy or using TPU are crucial here. But simply loading everything into memory isn't an option, so we have to be smart about how we process it. The TF Data API is your best friend. It allows you to build efficient data pipelines that can handle the load and process data in batches. Think about techniques like parallelization and profeshing to really speed things up. And don't forget state management. Time series have a memory of past events, so using stateful layers within TensorFlow will allow your models to learn those dependencies. Okay, let's talk about how AI models actually learn. They use something called a loss function. Think of it as a teacher telling the model if it's doing a good job or not. Most frameworks come with standard loss functions like cross-entropy for classifying things or mean-squared error for predicting numbers. These are great starting points, but sometimes you need something more tailored to your specific project. A custom loss function is exactly that. It's one you create yourself. It lets you define exactly what matters most in your model's performance. So, built-in functions are general and ready to go, while custom ones give you maximum control and flexibility, but they require a little more coding. Okay, let's talk about how TensorFlow handles those huge datasets and complex models. Sometimes, a single batch of data just won't fit in your GPU memory. It's like trying to carry too much luggage. That's where gradient accumulation comes in. Basically, instead of processing everything at once, we break it down into smaller chunks or mini batches. We calculate the gradients for each mini batch and then cleverly add those updates together before applying them. It's like saving up your steps. You don't take all the steps right away, but when you've saved enough, you take a big leap forward. This lets us effectively use a much larger batch size without blowing up our GPU memory. Okay, let's talk about going beyond the usual loss function in generative AI. Often, we don't just want a model to minimize the error, we need it to genuinely understand and represent the data well. This means creating custom training metrics that look at the whole dataset. The challenge is that standard losses treat each example separately, which isn't ideal for tasks where the overall quality matters, like generating coherent text or visually appealing images. To do this, you first need to clearly define what good looks like in your specific task. Then, you'll build a function that takes your entire dataset as input and calculates a score based on those criteria. Finally, integrate this new metric alongside the traditional loss during training, carefully adjusting how much weight each component gets. Okay, so let's talk about how TensorFlow is getting a serious upgrade thanks to something called MLR. Basically, MLR is like a universal language for computer code. It allows us to represent operations at different levels of detail. Initially, TensorFlow had its own way of doing things internally, but now they're adopting MLR to improve performance and flexibility. This means faster inference times, better support for specialized hardware like TPU, and easier adaptation to new technologies. It's all about making TensorFlow even more powerful and adaptable in the long run. Okay, let's talk about how we train these massive AI models. We can do it in a couple of ways, using multiple GPU on one computer, or spreading the training across several computers altogether. When you're using multiple GPU on a single machine, what you're essentially doing is splitting up the work. Each GPU takes a chunk of the data and processes it at the same time. But there can be memory challenges with this approach. You need to make sure your main computer has enough RAM to handle all those calculations. Then, if we're using multiple computers altogether, we're talking about model parallelism, where the model itself gets broken up. This helps us avoid running into memory issues on individual GPU, but introduces communication overhead between the machines. Frameworks like PyTorch and TensorFlow are really helpful here, providing tools to make this process much easier. Okay, let's talk about how we deal with text that isn't all the same length, like a sentence versus a paragraph. In NLP, many models need fixed size input, but naturally, sequences vary in size. That's where sequence masking comes in. Basically, we temporarily hide or mask certain parts of the text during training and inference. We first break down the text into tokens, think words or pieces of words. Then we create a mask that tells the model which tokens to pay attention to and which ones to ignore. The model learns to predict the masked parts based on the surrounding context, allowing it to handle variable length sequences gracefully. Okay, let's talk about how transformers know where words are in a sentence. Because they use attention, they don't naturally understand that dog comes before cat. So, we need to tell them. That's where positional encodings come in. TensorFlow uses sinusoidal functions, essentially using sine and cosine waves of different frequencies to represent the position of each word. It's like a unique fingerprint for each spot in the sequence. These fingerprints are then added directly to the word embeddings, giving the model vital information about order. You can see the formula right here. It's based on these oscillating functions and how their frequencies relate to the embedding dimension. Okay, so when you're taking a powerful AI model like GPT or Stable Diffusion and applying it to something really specialized, say medical imaging or legal documents, just throwing it into the deep end isn't always the most effective strategy. Instead, we recommend using a technique called curriculum learning. This means starting with simpler tasks related to your domain and gradually increasing the difficulty. Think of it like teaching a child. You wouldn't start by asking them to write an entire novel. Then, there's progressive alignment, a staged approach where we first align the model to a general understanding of your domain with smaller data sets, then refine it progressively using more specific information and tasks. Finally, carefully consider how you augment your existing data. Adding examples that truly capture the unique characteristics of your target domain can make a huge difference. Techniques like low array are also great for efficiently fine-tuning these large models without needing to overhaul them completely. Do you have any questions about this approach? Okay, let's talk about keeping your data pipeline running smoothly when you're training these massive AI models. It's not just enough to have the data, you need to make sure it gets to the model quickly. We want to focus on a few key metrics, things like how many samples we're processing per second and how long it takes to handle each one. Keeping an eye on error rates and resource usage, like CPU and GPU power, is also really important. Now, there are some practical ways you can boost your throughput. You'll want to experiment with different batch sizes, finding the right balance between speed and memory. Optimizing how you clean and prepare your data makes a huge difference too. And for very large pipelines, consider splitting them up across multiple workers or GPU using something called pipeline parallelism. Don't forget caching frequently used data to avoid constant trips back to the source. Finally, set up monitoring tools like TensorBoard or weights and biases to track everything in real time and let you spot bottlenecks quickly. Okay, let's talk about how TensorFlow uses different kinds of processors to speed up its AI models. First, we have the CPU, your regular computer processor. It's really good at doing lots of different things at once, but it's not ideal for the huge amounts of math involved in deep learning. Next up, a GPU. These were originally designed for video games, but they're fantastic at running calculations in parallel. Think of them as having thousands of tiny workers all working together. Finally, we have TPU, which are custom-built chips specifically created by Google to handle the massive matrix operations that deep learning relies on. They're even faster than GPU for this type of work and are especially useful when training really big models. Okay, so when we're training these powerful generative AI models like GPT or Stable Diffusion, sometimes things go a little haywire. Specifically, we might encounter what's called exploding gradients. Basically, the error signal during backpropagation becomes ridiculously big, and it can really throw off your training, even stop it completely. It often happens because of how large our learning rates are, or maybe the initial values of our model's weights aren't set just right. Luckily, there are a few things we can do to debug this. The simplest first step is usually to dramatically reduce our learning rate. Then, something really useful is gradient clipping, which limits how big those error signals get during backpropagation. Also, making sure that the model's weights are properly initialized can help prevent problems down the line. Finally, using techniques like batch or layer normalization can make the entire training process much more stable and less prone to these explosive issues. Keep an eye on your loss function. A sudden spike is usually a sign something's up. Thank you for watching.